This video describes a 7-day code challenge. So what you want to do is go to this website, syncexpress.com/7day.zip. You can download that file. This zip file will contain a PDF with instructions and a couple of different MATLAB files and a couple of Python files. And the idea is that you start with this file. It's called problem sets, either the MATLAB version or the Python version. And you go through 7 days. There are 7 exercises, and each day you do one exercise. Now, of course, I'm not sitting next to you, tracking you down, so you can do all 7 in one day. You can do all 7 over 2 weeks, one every other day. But I recommend doing one a day because it's good to get into a daily habit of coding. If you code at least a little bit every day, then your coding skills are going to improve steadily over time. Okay, so what I'm going to do first is just briefly explain each one of these exercises so that it's clear, and then I'm going to walk through my solutions in MATLAB and also in Python. Exercise 1 is to draw what I call an O face using circles, and here the idea is that you're only allowed to use the functions sine and cosine. And you want to draw a face that looks like this. So you can see that it's a bunch of circles, well, 3 circles and 1 oval, and I created all 3 of these using sine and cosine. Exercise 2 is to generate a fake sentence that contains 6 words. Each word has 4 letters, and the letters are just totally randomly selected from anywhere in the alphabet. So here you see an example of that. These are just randomly selected strings of 4 words, and there's 6 of them put together. So exercise 3 is to generate random numbers between 11 and 23.5 in steps of 0.5. Now you can pick how many numbers from this population you want to generate, but the idea is that you can only spit out numbers that are between 11 and 23.5 in steps of 0.5. So here you see an example, and all these numbers are in steps of 0.5. Then we get to day number 4. So on the 4th day, you want to take these 2 equations and graph lines corresponding to the 2 equations. And the idea is that this is a system of equations. This is a system of coupled equations. And if you represent these 2 equations as lines on a 2-dimensional plot, then you want to look for whether those lines intersect. If the lines intersect, then the system has a solution. And if those lines don't intersect, then this system is inconsistent. It has no single solution. All right, so then we get to exercise number 5. And that is to test the claim, which comes from linear algebra, that the eigenvalues of a diagonal square matrix are equal to its diagonal elements. So let's see, I have an example of that. So here you see an example of a diagonal matrix. So a diagonal matrix is a matrix that has all zeros except for the diagonal going from the top left down to the bottom right. So these contain non-zero values, and all the other elements in the matrix are zeros. And you have to make sure that this is a square matrix, so it has the same number of rows and columns. And then when you compute the eigenvalues of that matrix, you will find that those are equal to the diagonal elements. So what I'm printing out here in this matrix are, in the first column is the eigenvalues, the second column is the diagonal elements, and here I actually said the first column minus the second column, which all equals 0 because these are the same. So this is one demonstration of this claim. Okay, and then number 6, exercise number 6, is to create a 40 by 40 checkerboard image. So let's see. Oh yeah, I forgot to show you this, but this was the graph result of exercise 4. Okay, so then exercise 6 is basically to create this checkerboard image. There's a couple of different ways that you can create a 40 by 40 checkerboard. There is actually a formula. That's the easiest way to do it. There is a specific formula that will give you this result. So you can see if you can figure out the formula, or you can look it up online. All right, and then on the final day of this code challenge, you want to draw a circle using the formula, apologies for the incorrect formatting here, the formula x squared plus y squared equals 1. So that's going to look like this. Now, you've already drawn a circle up here with number 1, but here you're using the functions sine and cosine to draw the circle, and here I want you to use the formula x squared plus y squared equals 1, not the trigonometric functions. Okay, so good luck working through all of these exercises. If you want a little bit of a hint to get you started, then you can download this zip file. So what I encourage you to do now is pause the video, wait 1 week, go through all these exercises, 1 per week, and then come back to this video and you can watch me do the solutions. First, I'm going to go through all the solutions in MATLAB, and then I'm going to go through all the solutions again in Python. So if you prefer to use Python, then you might want to skip forward for a few minutes until I switch to Python. All right, so let's get started with MATLAB. I'm going to close all of these figures, give us a little bit more space here. And so the idea here is we are going to draw cosine by sine, and that's going to give us a circle. So what we need here, the key parameter here is theta, which I'll call variable th. So that's going to be linearly spaced numbers between 0 and 2 pi, and it doesn't really matter how many numbers you have, but 100 turns out to be a pretty reasonable number to give us a nice smooth circle. All right, so I'm going to start this on figure 1, and let's see, we start by plotting the cosine of theta by the sine of theta. And let's make this a black line that's a little bit thick. Let's see. All right, so far looking good. It actually looks a little bit more like an oval than a circle, but that's because the axes are not equal. The axes are rectangular. So I'm going to write axis square and then also turn off the axis. Okay, so now we get a nice looking circle. Now we need to draw some eyes. So the idea is that the eyes are drawn exactly the same way as this line, except that we make them smaller and we offset them by an x coordinate and a y coordinate. So let's start by making them smaller. So to make the circle smaller, you just divide by some number. So for example, if I would divide by 2, so I'm dividing both coordinates by 2, you can see that we get a circle with 1/2 of the radius. So for the eyes, what I did is set this to be 1/5, like this. Okay, so this is one eye, but we don't have a cyclops. We have a normal looking face with 2 eyes. And so they need to be, a little bit higher, and we'll put this one up here off to the left. So the way we do that is by thinking about that the cosine corresponds to the x-axis and the sine corresponds to the y-axis. So on the x-axis, we want to shift the center of this circle by some amounts, and it turns out that minus 0.4 is the amount that I used. And of course, you can use some other number, but this is just what I used. So now this is still sitting on the y-axis, so we need to offset it on the y-axis as well. And here I used plus 0.4, so 0.4 plus, plus should be here, of course. Okay, so that's for the one eye. Now the other eye, I made red for no particularly good reason. So now the y-axis offset is the same, and the x-axis offset is the same, except it's on the other side. So let's make this red and a nice thick red eye, because I don't know, maybe this guy got into a fight or something like that. Okay, so that's for the 2 eyes. Now we need to draw the mouth. So the mouth is going to be centered on the x-axis, and on the y-axis it's offset by a little bit, so it's a little bit lower. So now this is fine, except what I actually drew was an oval. So here he looks a little bit surprised. Maybe he's surprised that he got punched in the eye. But so to make this an oval, essentially we need to scale the cosine and the sine differently. And in particular, we want the sine, which corresponds to the y-axis, to be relatively compressed, and the cosine to be expanded. So the way that I'm going to do that is by dividing the cosine by 2. So now the x-axis variable is less compressed, and the sine axis variable, or the y-axis, is more compressed. All right, so that is the successful completion of this part of the project. So this was day 1. Here is the solution to day 2. Now, to generate all of the letters, what you can do is something like, A, B, C, D, E, F, G, and so on. But it turns out that in MATLAB, there's a bit of a shortcut. You can say string A through string Z, like this. And that is going to give you all of the letters, just like this. So now what we need to do is loop through and pick out 4 letters randomly from this set of 26 letters 6 times. So let's see, I'm going to initialize sentence to be the empty set, and then I'm going to loop over word. So word equals 1 through 6, and then what I want to do is pick random letters, and so I'm going to write rand indices. So what I'm going to do here is just generate 4 numbers. These have to be integers because these are going to be indices into this vector letters. So I will use the function rand I. And the way that this function works is you specify a number. Let's see, I'll even start down here just to introduce you to this function. So rand I, let's say 5. So what this is going to do is generate a random integer between 1 and 5. But let's say I want 2 numbers. So you could think of writing 2 like this, but that's actually going to give you a 2 by 2 matrix. So now I'm going to write 2, 1. That's going to give me a matrix of size 2 by 1, and everything in this matrix, or all the elements of the matrix, are randomly selected integers between 1 and 5. So with that in mind, we want to select random integers between 1 and the length of this vector letters, and we want 4 of these because we are creating 4-letter words. Okay, and let's just see what that happens to be like here. Okay, so this happens to be these numbers, and then we can type letters rand indices, and this is our first random word. And maybe this is pronounced Xiod or Zyod. It sounds quite science fiction-y, doesn't it? It's like the land of Zyod. Anyway, so what do we want to do with these letters? We want to put them into the sentence. So I'm going to use the cat function. So I'm going to concatenate the sentence, and we're going to concatenate row-wise, so make sure that the letters all print out in a row instead of in a vertical column. So I want to concatenate the sentence with the letters and rand indices. Okay, and then I reset, or I redefine sentence to be this thing. And then let's just display this. Now it turns out that this is not totally correct the way that I've just done it. And that's because there are no spaces. We need to add spaces. So what I'm going to do is another concatenation, but this time using square brackets for concatenation, and I'm going to concatenate a space in between a set of single quotes like this. All right, and then we get our word, and I'm not going to embarrass myself by trying to read this out loud. I will let you do the embarrassment for me. All right, very nice. That was number 2. Maybe that's Tuesday. Now we get to number 3, maybe that's Wednesday if you're really doing this once per day. And what we want to do here is generate random numbers between 11 and 23.5. So I'm going to start by generating this distribution. So num pop for a number population. And that's going to go from 11 to 23.5, except that when I write the code just like this, it's actually going to give me integer steps. So I want to go from 11 to 23.5 in steps of 0.5. So that's going to look like this. Nope, not like that, sorry. I don't know why I wrote 11.5. This is in steps of 0.5. Here we go. This looks better. So now you can see we start off at 11 to 11.5, 12, 12.5, and so on up to 23.5. And now from here, we want to generate randomly, let's say 10 of those numbers. And now I'm going to generate these random numbers, or pick from here randomly, essentially the same way that I did here using the randi function. So let's write numpop. I'm going to do this all in one line of code. Rand I. So I want to generate random integers between 1 and the length of numpop. And this should be an n by 1 matrix, in other words, an n element vector, of random integers between 1 and the length of numpop. Now notice I'm actually writing this slightly differently than how I did earlier. So up here, I gave 3 inputs into the randi function, and the second 2 inputs, or the second and the third input, were the 2 sizes of the matrix. Here, I'm only inputting 2 inputs into the randi function, and the second input is a 2-element vector that contains the matrix size. So this is actually equivalent to this. I just wanted to introduce you to 2 different ways of doing this. All right, and there we go. Randomly selected numbers between 11 and 23.5. All right, so we are doing great. Let's see, here is the 4th exercise. So we have these 2 equations, and we want to make a plot of them. So I'm going to start by defining x. So x is going to be linearly spaced numbers between -3 and +3, and let's go for about 52 steps between +3 and -3. There's no particular reason why this is going to be 52 and not 50, but you know, it's good to stick to interesting numbers sometimes. Now, there isn't really a trick to getting this to solving this problem. You just have to appreciate that the way to do this is to rewrite these equations to solve for y. So we want to write something like y equals 3x plus 5. So you can see that all I'm doing here is rewriting this first equation so that it is set equal to y. So I'm just moving the 3x to the other side. Now, of course, I have to say 3 times x, and I'm actually going to call this y1 so that we have y2 equals, now we already have the 2 on this side, so that's 2 times x. And now we need to subtract the 3 to get the 3 over here. So 2x minus 3, but then we have a minus 3y. So what I want to do is divide both sides of this equation by -3, and that's going to isolate y on the left-hand side. So here I have to divide by -3, so I'm going to say divided by 3, put a minus sign in front. Here we divide by -3, so divide by 3, and then this will change into a plus sign. And now you could also just change this to 1, of course. 3 divided by 3 is 1. So let's see, I'll put this in figure 4. And we want to plot x by y1 and x by y2. And let's make these lines nice and thick. So there you go. That's looking pretty good. Now, first of all, you can already see that the 2 lines intersect. That means that there is a solution to this system of equations. And that solution is approximately x equals -1 and y equals 1.7. All right, so what I want to do now is basically just spend a moment to make this plot look a little bit nicer. So I'm going to set the y-axis, so y-lim, to be from -4 to +4. Oops, this is set, not get. And let's see, I'll make the axis square, and I'll turn the grid lines on. This is looking better. And now the last thing I want to do is put some black dashed lines along the x equals 0 and y equals 0 lines. So let's see, I think I'll do that down here. So I want to plot a line. It's going to go on the x-axis from basically the limits of x. So it's going to go get current axis x lim. So notice that this is going to return the x-axis limits, and that's exactly where I want to draw this line from minus x to plus x. And then the y-coordinates for this line are 0 and 0, and I'm going to draw this as a black dashed line. So that's for x, and now for y, this is essentially going to be the same, except I swap the order here, and of course what I care about is the y-axis limit. All right, looking very nice. I am pretty happy with this solution. So now on to number 5. So this was about eigenvalues of a diagonal matrix. So I'm going to start with by defining the size of the matrix. So this is going to be a 7 by 7 matrix. Let's see, and to create this matrix, I'm going to use the function diag. So this is a fairly flexible function, diag. The way that I'm going to use it here is by specifying only the diagonal elements, so let's say 1, 2, 3, and then MATLAB will automatically generate a diagonal matrix with these elements on the diagonal. So this is 1, 2, 3. To make this a little bit more interesting, I'm going to use the randi function again, and let's generate random integers between 1 and 100, and there's going to be n of them like this. So here's our diagonal matrix. And then to extract the eigenvalues, I'll call this variable evals, and that's just the function eig. Now, if you request 2 outputs from the eig function, you're going to get both the eigenvalues in a matrix and the eigenvectors. But in this case, we really only care about the eigenvalues, so we can only get 1 output from the eig function, and that returns a vector like this. All right. Then the final thing that we want to do is print out the diagonal elements, the eigenvalues, and the difference between them to show that those are 0. Now, the thing is that there's no guarantee that eigenvalues are going to be sorted in the same order as the diagonal elements here. So therefore, we also need to sort all of the diagonal elements and the eigenvalues. So sort, and then let's start with the diagonal values. Now notice here, I'm actually using exactly this same diag function, except here I input a vector and it produces a matrix, and here I input a matrix and it extracts only the diagonal elements. So it's a pretty flexible function. So sort the diagonal elements of M, sort the eigenvalues, and then we want the difference between these two, which I'm going to write like this with a minus sign. And then we see that the diagonal elements of M are equal to the eigenvalues of M. So that's actually a pretty neat property of diagonal matrices that you would learn about in a linear algebra course. Very nice. So that was day 5. Maybe this is Friday if you started on a Monday. Now we get to the weekend, which is where the fun starts. So let's create this random matrix. So it's going to be 40 by 40. So I'm going to specify n to be 40. I'm going to initialize this image to be zeros, and then we want n zeros. Now the formula for computing or creating a checkerboard image is -1. Let me put this in a comment here. So it's -1 to the power of I plus j, where I and j are the row and column indices. So this is the general formula that you use. You just have to be careful with the order of operations because the exponent takes precedence over subtraction. So in fact, if you write out a formula like this, then this is just going to compute 1 to the power of, whatever, which is always going to be 1, and then minus that thing. So this is going to produce a matrix of all 1s. So we use parentheses here to prioritize the -1 over the exponentiation. All right, so let's see. I'm going to create a double for loop. So for I equals 1 to n, and for j equals 1 to n, and then we say that the ith, jth element is equal to this formula. And then, let's see, I'll put this in figure 6. And let's say image, the image, and I'm going to set the color map to be gray. All right, so there you go. I'm going to make this actually a square axis, axis square. All right, so that is the solution to this problem. It turns out there's a shortcut in MATLAB using linear algebra that you can use to get all of this code to work without having to use a double for loop. So that looks like this. So initially it's the same. We still have -1, and then we want times, and now this is, or not times, but to the power of. And now here I'm going to put in a matrix. So that's why we need the dot caret instead of just the regular caret. And so what I'm going to do here is basically expand all of these I plus j's using some matrix notation. So this is going to be 1 to n, make this a column vector plus 1 through n as a row vector. And MATLAB is going to automatically expand this into a matrix. Now, this is something that only relatively newer versions of MATLAB will do. I forget exactly which version they started allowing this, but if you have a slightly older version of MATLAB, then this is actually going to give you an error. But otherwise, with the newer versions of MATLAB, this is going to work. So now you see I commented this out, ran the cell again, and we got exactly the same result. Very nice. So now the last exercise is to draw a circle using the formula x squared plus y squared equals 1. Now the key to this exercise, the key to solving this, is again to solve for y, and then you get into a bit of a weird situation where it's going to look something like this. So to solve for y, you subtract x squared. So this is going to be 1 minus x squared. And then you have to take the square root of both sides. So we take the square root of both sides of the equation, which gives us y equals the square root of 1 minus x squared. And now, oops, I have to define my x term. So x is linearly spaced numbers. Now we can look at this formula to see what the bounds on x need to be. So if x is larger than 1, then this term inside the square root is going to be negative, which means the square root is going to be not a real number. It's going to be a complex solution. So therefore, x cannot be larger, or x squared, I should say, cannot be larger than 1. So I'm going to set x to go from -1 to +1, and let's try 100 steps. All right, so let's plot this in figure 7. And let's see, so I'll plot x by y, and let's see how this looks. So it's not exactly a circle, is it? It looks like an arc. Now, part of the problem here is that the axis is unbalanced. So this goes from -1 to +1, and this goes from 0 to 1. So I'm going to say axis square, and then I'll also turn off the, maybe I'll leave the axis on for now. Okay, so why do we only get an arc instead of a circle? Well, when you think about what happens when you take the square root of both sides of this equation, then in fact we're only getting part of the solution here. So this is only the plus side. So this is like, when you take the square root of 4, the answer is +2 and -2. So here we actually need to separate this into two sides of this equation. So there's going to be, I'll call this yu for y upper and yl for y lower. And the lower part of the circle is minus the square root of 1 minus x squared. So this plot needs to go like this. X comma y1, this is x upper, and x comma y lower. All right, so now this is looking good. That's a full circle. Great, so I hope you enjoyed this. I'm curious to know if you actually did this over 7 days, or if you did it all in one setting, or maybe did it over 7 years. That's probably not super efficient. Nonetheless, however you solved this exercise, I hope you enjoyed working through this. Next, I'm going to switch to Python, and I'm essentially going to walk through the same solutions, but using the Python language. So here we are in a Jupyter IPython notebook. This is the environment that I will use to solve all of these problems. So throughout these 7 challenges, I'm going to be using NumPy and Matplotlib. So let's first import those guys. So now challenge number 1 was to draw basically just this face. So what I'm going to do is begin by defining the angles that I'm going to use. So I'm going to define angles that go from 0 through pi and all the way up to 2 pi. So I'll call that variable th for theta. So that's going to be numpy.linearly spaced numbers between 0 and 2 times pi. And let's go for 100 steps between 0 and 2 pi. So I will start by plotting the cosine of theta by the sine of theta. And let's see, I'll make this a black line, and let's set the width of the line to be 2. All right, so now plot.show. So that's actually going to erase this thing here, but that's fine. We're going to redraw it. So we kind of have a circle. It looks more like an oval than a circle, but that's because the axes are not equally lengthed. So the x-axis is actually longer than the y-axis is tall. So to fix this, I'm going to write plt.axis square. Now we get a circle. And then I'm also going to turn off the axis. So plt.axis off, like this. All right. So now the idea for the eyes is essentially the same. So we use the same formulation, except that the circle has to be smaller and it has to be offset. So I'm going to start by copy pasting, and let's start by making the circle smaller. So to make the circle smaller, all we have to do is scale down the cosine and sine coordinates. So I chose a value of 0.2, or divided by 5. So we can already see what that looks like. So now we have a circle with the same origin as this larger circle, but the radius is 1/5 compared to the larger circle. Okay, so what we need to do now is offset this. I'm going to put this circle, this is going to be the left eye, so it has to move up here. So I need to shift it on to the left on the x-axis, and I need to shift it up on the y-axis. So cosine corresponds to the x-axis, so I'm going to write plus 0.4, and let's already try that. Oops, I meant to write minus 0.4. So shift it to the left, and now we need to shift it up, and I also made this offset to be 0.4, like this. So there you go, that's the left eye. And now the right eye is essentially the same. The y-axis offset is the same. The x-axis offset is now going to be plus 0.4. And I'm going to make this a thick red line, because maybe this guy got into a fight, he got punched in the eye. All right, so now we have the 2 eyes. Now we need a mouth. So let's see, I'm going to paste this again, and this is now going to be, so let's get back to the origin here. So here we have a small circle at the origin. This looks more like it would be a nose. It looks a little bit too close to the eyes. So one thing that I want to do is shift this down on the y-axis. I used minus 0.3. And now, he looks a little bit surprised. I want him to be grimacing a bit more. So what I'm going to do is stretch out the cosine without stretching the sine. So in fact, what I meant to say is I'm going to stretch this less. So right now it's stretched a lot, and I'm going to divide it by 2. So the cosine axis is stretched only by a factor of 2, and the sine axis, or the y-axis, is stretched by a factor of 5. All right, this looks great. We have our O face here. Let's move on to challenge 2. So what we want to do to solve this challenge is come up with all of the letters in the alphabet and then randomly select 4 of them and then repeat that 6 times. Okay, now you could set this up like this. You could say, A, B, C, D, E, F, G, and so on. However, there is a slightly easier way to do this, and that is by importing a function called string, and then there's a method in string that is letters equals string.ASCII, and then I'm going to write ASCII lowercase. And let me show you what this looks like. So this gives us a character string of all the letters, lowercase letters in the English alphabet. All right, and so from there, what I'm going to do is loop over words. So for word in range 6, so this is going to loop over the numbers or integers from 0 to 5, because that's basically how this range function works. It will count, it will export a range or a set of integers that go from 0 by default, unless you specify some other number here. So this would go from 0 up to 5 because the second boundary is exclusive. So we want 0 up to 5, so that's going to go like this. Okay, so what do we want to do inside this for loop here? Well, first I'm going to pick the random letters, and then I'm going to create a word and put it in the sentence. Okay, so let's start by picking 4 random letters. Actually, what I'm going to do is not pick the random letters per se, but this is going to be random indices. So I'm going to pick some random integers between 0 and 25, or however many letters you have in the alphabet you're working with. So I'll call this rand idx for random indices, and that's going to be numpy.random.randint. So we want random integers between 0 and the length of letters, and we want 4 of them. So let me just show you what this is going to look like. So rand idx. Okay, so here you see for each iteration in this loop, I'm just printing out the 4 randomly selected integers that go from 0 up to 25. So that gives us 26 letters to choose from here. Okay, and then what we want to do is loop through all of these indices and basically get out, the 6th letter, or this is actually the 7th letter, right? Because Python starts counting at 0. So let's see, I'm going to do this in a loop. So for I in rand idx, and actually let me get rid of this print thing here. So the way that I'm going to set this up is by saying sentence equals, and then I want it to be sentence plus letters I. Now I haven't created sentence yet, so this is going to give me an error. So I need to initialize sentence to be an empty string like this. So sentence starts off being empty, and then I add to the sentence 1 letter corresponding to the ith index that was selected up here. Now this is fine, but in Python we can do this slightly more efficiently by getting rid of this and putting the plus sign here. So this plus equals indicates to Python to reassign the entire variable sentence, this vector of letters, with itself, and then adding to the end the letter. Okay, so this is actually not quite complete, but I want to print it out anyway so you can see what it's going to look like. Okay, so the reason why it's not yet complete is that we haven't added any spaces, so this just looks like one really long word. So what I'm going to do is here, after this loop ends, I'm going to write sentence plus equals, and then a space like this. All right, very nice. So that is the successful completion of exercise 2. So maybe this was Tuesday if you're going through these one a day and you started on Monday. On to number 3. So here we want to generate random numbers, and I don't say how many, but some number, maybe 5 or 10 random numbers drawn from a population of numbers between 11 and 23.5 in steps of 0.5. So here you see an example. There are numbers selected between 11 and 23.5, only going in steps of 0.5. So let's see, I'll start by saying we want to generate, how about 9 numbers? Because 10 is, I don't know, 10 is it's too much of a normal number. Let's go for 9. So I'm going to start by generating the population of numbers that we are going to draw from. And I'm going to do this using the function arange, which is in the NumPy module. And the way you use this function is you specify the lower bound and the upper bound, and then the increments or the stepping size between them. So let's already see what this looks like. Pop num. Aha, so this is pretty interesting. You see, it starts at 11, it goes to 11.5, and so on, in steps of 5 up to 23. We're missing the final step of 23.5. And the reason for that is that Python always has exclusive upper bounds, not inclusive upper bounds. So if you actually want to get up to 23.5, you need to write 24. So it's a little bit confusing at first, but you just have to keep in mind that Python always has exclusive upper bounds on these kinds of functions. All right, so then we want to, so I'm going to generate some random integers similar to what I did in this problem up here. So let's say rand idx equals numpy.random.randint. And now, again, we want randomly selected integers between 0 and the length of pop num. And I want n of these numbers. And then I'm just going to print out population of random numbers. And then we want, in particular, these random integers. Or random indices, sorry. Okay, so that looks good. And then we can run this a few times. You see that it's different each time. All right. Onwards. So now we get to problem 4. Here the idea is we have these two equations. We have a system of equations, and we want to graphically illustrate this system of equations by representing each individual equation as a line. Now the reason why it's useful to graph these two equations is that we know from algebra that if this system is consistent, if there is a solution to a simultaneous solution that satisfies both of these equations, then that means that their lines intersect. So we can see that the two lines cross here, they meet at a point, and that means that this system of equations actually has a solution. All right, so drawing this function isn't so difficult. The main tricky thing is you have to realize that you have to re-express or rewrite these equations to make them be a function of x. A function of y, I meant. So I'm going to start by defining a variable x that's going to be used for plotting. So that will be linearly spaced numbers. You can see on this plot it goes from -3 up to +3. So I'm going to continue with that tradition. So -3 to +3 in 50 steps. Now, I know you're probably thinking that 50 is a really boring, straight number, so okay, fine, I'll change it to 53. There. I hope you're happy. Let's see. Now we need to create the functions. And essentially what we want to do is rewrite these to be a function of y. So I will write y1 equals, and y1 because the other one is going to be y2, of course. So y1 equals, and then we just have to subtract 3x from both sides of the equation, add 3x from to both sides of the equation. So that gives us 3 times x plus 5. So there you go. That's our first equation. Then the second one, y2 equals, now this one is a little bit more involved. So let's start with this. So we still have the 2 times x. That part's pretty straightforward. Then we have to subtract 3 from both sides, so we get -3. But now we actually have -3y on the left, and we just want y and nothing else on the left side of the equation. So we have to divide both sides of the equation by -3. So that gives us on this side minus 2x divided by 3. And then over here, this minus turns into a plus, and then we have 3 divided by 3, which of course is just 1. All right, so with that in mind, now we can plot. So plt.plot x by y1 and plt.plot x by y2. And let's already see how this looks. All right, looking pretty good. There's a couple of things that I want to improve about this plot. One is you can see the axis limits are different for the x-axis and the y-axis. It makes it a little bit harder to interpret. So I'm going to make this plot square, the axis square. And then I'm going to set the y limit to go from -4 to +4. And I'll also set the x lim to be the same. So -4 to +4. Let's see. All right, this is looking better. I'm going to add a plt.grid. So it's going to say plt.grid on. Oh yeah, right. This is the older way to express this. It's actually just plt.grid, like this. Okay, this is looking quite good. Main thing I want to do now is add dark dashed lines, so black dashed lines here, to the x equals 0 and y equals 0 coordinates. That just helps us look at this graph a little bit better. All right, let's see. I think I'll do that down here. So let's write plt.plot. And now we want this line to go on the x-axis from -4 to +4. And on the y-axis, it's going to go 0 to 0 because it doesn't change on the y-axis. That's going to be a black dashed line. Beautiful. All right, and then copy paste, and then essentially we just need to move this. We just swap which axis gets the 0, 0 and which axis gets the -4 to +4. Cool. This looks really nice. And we see that this system of equations has a unique solution, has exactly one solution. So now on to the fifth exercise. So here we want to basically come up with a square matrix that is a diagonal matrix. So that's a matrix that has the same number of rows as columns, and diagonal means that it has all zeros on the off-diagonal elements and non-zero values only on the diagonal elements going from the top left to the lower right. Then we want to compute its eigenvalues and show that the eigenvalues are the same as the diagonal elements. And what you see here, what I've drawn here, is the diagonal elements and the eigenvalues and then the difference. So basically the first column minus the second column, and of course that is all zeros because these two are the same. All right, so let's begin. It's a little bit of linear algebra here. So I'm going to start by defining n. This is just going to be the size of the matrix. So I'm going to create a 7 by 7 matrix. So let's see, that matrix will be, I'm going to say numpy.diag. And now the way this function works is you can specify a vector, a list like this, and then Python is going to create a diagonal matrix out of this input vector. So this is fine, you could solve it like this, but I want to make these be random integers. So I'm going to write numpy.random.randint, and let's say random integers between, how about 1 and 97? Those seem like good range. Pretty arbitrary. Remember, actually, this will only go up to 96, really, if I write 97 here. But I like the way the 9 and 7 look next to each other, so I'll keep it like this. Okay, anyway, let's see how this looks. Okay, so we get a matrix with random integers on the diagonal and all zeros on the off diagonal. Of course, each time I run this code, we get a slightly different result. Great. And now we want the eigenvalues. So evals equals, this is also in the NumPy module, in the linalg submodule, and the function is called eig. So let's see what is in evals. Now we actually get two outputs from the linalg.eig function. So the output of this comes as a tuple. The first element in the tuple is the eigenvalues, and then the second element in the tuple is a matrix containing the eigenvectors. Now it turns out that a diagonal matrix has the identity matrix as its eigenvectors, but that is not what we want here. What we are most interested in here is only the eigenvalues. So I can write this like this, but I can make this a little bit easier by only exporting the first element of the tuple, or the first output of this function, in this fashion. All right, now what we want to do is compare all of these. My preference for the format of the output is in a matrix with 3 columns. And so in order to make a matrix with 3 columns, we need to actually convert these outputs, so the eigenvalues and the diagonal elements that I'm going to extract from this matrix, I need to convert those into a NumPy matrix from a NumPy array. So I'm going to call this mat.diag. These are going to be the diagonal elements of the matrix. So that's going to be numpy.diag m, And notice it's the same function, but here I'm inputting a vector, here I'm inputting a matrix, and the output is going to be the vector of diagonal elements. Okay, and now I also mentioned when I introduced this problem that it's good to sort them, and you can see in this example why it's good to sort them. There's no guarantee that the eigenvalues will come out sorted in any meaningful way that's related to the diagonal elements. So I want to use numpy.sort. So that's going to sort them. And then I need to convert them into a matrix. So numpy.matrix. Okay, and let's see what this already looks like. So matdiag. Okay, so this is a matrix, but this is a row. I want to make this a column. So therefore, I'm going to write .t for transpose, and now we get a column vector. All right, so quite a lot of embedded functions here, but you can see the end result is this column of sorted diagonal elements. All right, so that's for the diagonal elements. Now we want the eigenvalues, I'll call this eval, equals, and now let's see, so I also need to convert to a matrix, I also need to sort, and this is going to be the vector evals. All right, and then let's see, I'm going to start by concatenating these. So numpy.concatenate, and what I want to concatenate is the matdiag with mateval. So let's see what this looks like. Okay, so here we actually get one really long column vector, but that's concatenating along the wrong dimension. So therefore, I'm going to write axis equals 1, where the default is axis equals 0. So now we get two columns, and you can already visually see that these are the same. However, I'm going to add another column to this matrix here, and that's going to look like this. So matdiag minus mateval, and that's all zeros because these are the same. So this is a demonstration of the claim that the eigenvalues of a diagonal matrix are equal to its diagonal elements. Cool. So if you are following along doing one exercise per day, and if you started on a Monday, then you're now on the weekend. Then this is the exercise you completed on Saturday. I hope you enjoyed it. Of course, I also hope you did some, other interesting things on your weekend, not just solving Python problems. Let's see. So we want to create a 40 by 40 matrix that is a checkerboard like this. So n equals 40. And now I'm going to start by initializing the output matrix. Let's see, img equals numpy, initialize this to zeros, and it's going to be n by n. And now, essentially what I'm going to do is loop over all of the rows and all of the columns, and then apply a formula to each individual element. So for I in range, n, and then for j in range, n. It's a square matrix, so the ranges are the same for I and j. Okay, let's see. So we set the ith row and jth column to be -1 to the power of I plus j. That's the formula for creating a checkerboard matrix like this. It ends up being all +1s and -1s. So let's see if I did the right thing, or maybe I made a mistake somewhere. A little bit of foreshadowing. So let's see, im show, img and plt.show. Well, I do like purple a lot, so I'm pretty happy to see all this dark purple, but this is clearly not the right solution. In fact, it looks like every element here has the same value. Let's even print out this matrix and see what it looks like. So it's all -1s. So what is going on here? Well, what's going on here is the order of operations. So Python is prioritizing the superscripting over the minus sign. So Python is actually computing 1 to the power of, the row plus column index. And that's, of course, 1, because 1 to the power of anything is just 1. And then it's setting that to be minus. So what we need to do is say -1 in parentheses to this power. And now we get a good solution, and you can see these are also alternating +1s and -1s. Now I just want to change the color map here, so I'm going to write CMap equals gray, and that's going to give me a nice looking checkerboard. If you were playing checkers on a board like this, that would take a really long time. It would be a pretty long game. So final stretch, we get to the 7th and final exercise, which is to draw another circle using the formula x squared plus y squared equals 1. So this is different from the first exercise because there you were using cosine and sine. Here you're using this algebraic formula x squared plus y squared equals 1. So to draw this, we need to basically define this equation in terms of y. So y equals, then it's going to be 1 minus x squared. And then we need to take the square root because we want just y on the left. So we need to take the square root of both sides of the equation using numpy.square root like this. And then we can plot plt plot x comma y. So what does x have to be here? Well, just from looking at this formula mathematically, we can see that when x squared, when this term is greater than 1, then the inside of the square root function is going to be negative, and negative square roots are not defined, or square roots of negative numbers are not defined in the plane of real numbers, which is what we are interested in here. So therefore, x has to be between -1 and +1. So I'm going to write numpy.linspace -1 to +1, and I'm going to write 100, despite your protests that I shouldn't be using such a nice, neat round number. All right, so let's see how this looks. Well, it looks like it's an arc. It's half of a circle. So why is that the case? Why is that? What did we do wrong here? Well, we didn't really do anything wrong, but we are missing something. And what we're missing is that this is only half of the solution. And that's because, if I would ask you, what is the square root of 4? You could say 2, but that's only half the answer because -2 squared is also 4. So we need to write explicitly that there's going to be two solutions. I'll call this y, p for positive, and n for negative. So this is plus the square root and minus the square root. And that means that we also need to draw two lines here. So p and then x comma y, y, n, and plt, I'm going to set the axis to be square, and plt dot show. All right, so there you go. We have the positive solution and the negative solution, and together those make a circle. I'll turn the axis off here. Axis off. Very nice. So that concludes this 7-day code challenge in Python and/or in MATLAB. I hope you enjoyed it. And what I hope you got out of this is that by programming a little bit every day, your coding skills will improve considerably over time.